the major thing that we should put into consideration during the design is the slope of the pipes, as we have seen from the analysis of from the video. The slope, when the slope is not too, when the slope is not on the recommended height, or the slope is not good, we shall find challenges like clogging of the sewage or any materials in the pipe, which will reduce the pressure or the size of the water or any sewage that is coming through the pipes. Therefore, in the long run, we shall have challenges with our design of the whole system. And maybe another thing is the components that we throw anyhow in our pipes or in our drainage systems. Those are the very materials that in the long run make damages or broke our channels. Yeah. So there are so many challenges I've encountered or I've analyzed in that video. I think that is what I can share. Maybe I give others a chance to share also. Thank you, James.
Absolutely. Thank you. Thank you very much, engineer. And yes, I agree with you. That sizing of our the pipe of our sewer of our sewers is very important. Most importantly, the slope. So what Sam is saying, and thank you very much, is when you're designing your sewers, you must ensure that, I think this is what Byron taught us previously, that you must ensure that your sewer will get to the self-cleaning velocity at least once every day. This ensures that your sewer line is self-cleaning, and you don't need, it will not block in the long run due to the debris. Thank you very much. I'll give it out to someone else. Let's get to hear. What are your thoughts about this? We can also be using the chat box. We can also be using the chat box. So someone else, please take it away. What have you learned about about sewer from the video? Let me get to hear. Who is that?
Yes. Good evening, engineer.
Good evening, engineer. How are you?
I'm doing well. Well, from me, what I've understood from the video, you've said some of it
Please
is about.
introduce yourself. Please introduce yourself. Please introduce
Okay.
yourself.
Okay, I am Simbarashe Mtuta from Zimbabwe. I'm a civil engineer student.
Thank you. Proceed.
So as I was saying, one of the things that I've managed to take out from the video, they've said something about it is the velocity. That when we are designing our sewer system or our sewer pipes, we should take velocity into consideration. We need to make sure that the velocity that we are designing for is greater than the self-cleansing velocity. This is the velocity that makes sure that the particles do not settle, as this might block the pipe. And also the velocity should not be too high, should not be greater than the scoring velocity, because this will damage the pipe at the bends when the velocity is too high. And one way to control the velocity is through controlling the slope and maybe the sizing of the pipe that also controls it. I think that's it for me.
Absolutely. Thank you very much. That was a brilliant one and very comprehensive. That we should also be able to consider the velocity, the scoring velocity, because also you don't want to damage your infrastructure. So thank you very much. I know Baron is best suited also to respond to most of these. So thank you very much. One more person. Let's get to here. Introduce yourself, and then you can give us a piece of your mind. This is our community. So come on, take it away.
Good.
Yes, Justin.
Good evening, engineers.
Good evening.
Good evening, everybody. My name is Justin Leslie. I'm a graduate engineer from Barbados. And when I was reviewing the information on the video, what was interesting to me is that when you approach a stream or a river, you can use siphons to cross the underside of the river, but the siphons must be of smaller dimension than the size of your sewer pipe, so that, the flow of a greater velocity. What? Can you still hear me? I'm seeing a
Yes,
whiteboard on
Justin,
the
we can
screen.
hear you. Yes, we can hear you.
Okay, right. So the ciphers must be of a smaller diameter than the original pipe. Velocities are higher, and this is them plugging because when they dip, the cells can settle there because of the velocity. So you can use either two cross.
Apologies for that, Justin. Well, it looks like we lost you. You are not audible. But I think your point is whole.
Yeah.
Thank you very much.
Yeah. Mm-hmm.
Justin,
Thank you very much.
Justin, thank you very much. So what I'm hearing is he has been intrigued by the siphon, where we use it inverted siphon, where it is used to cross river streams. And that's a fantastic one. Yes, that's a great technology because there's a relationship between the diameter just from the continuity equation. So thank you very much, Justin, for that. Edson Budala, I can be able to see you here. Let's also get to hear from one lady. Come on. Lady engineers, how are you? Where are you? Can you share with us what is your perspective from the video that we just played? So yes. Ladies, where are you? Lady engineers, where are you? Let's get to hear from you. Diana, I can see you here. Diana, I can see you here. Natasha, I can see you here. Hannah, you're there. Claire, you're there. All right, amazing. So I will give a summary of probably what I've been able to collect from all of you people. Number one, from the video that has been taught, that we've shared, the most important point is the public health. So for us as engineers, I think, remember it was a certain consulting engineer, we were having a meeting and we were reviewing the proposal that the institution of engineers proposed following some plans. And one of the key things that was highlighted was the public health of the people. So you will some may argue with us that engineers are the custodians of the public health of our communities. When we talk about the public health is when we don't design our sewer systems as they should, when we do not manage and maintain our sewer systems as per the standards, the biggest risk is poisoning our people, poisoning the population. When we spill sewer all over the town, when they mix with the drinking water and all of these, the kind of contamination that we can have. And that is the first point. The second point was about urban development. So most parts of the country or of the world are undergoing rapid urbanization. There is a lot of development, and that means as more people are moving to urban areas, it means also our existing sewer systems are constrained, or sometimes they get overwhelmed. So it is also good for us to keep designing our sewer systems with the future. We are designing for the future. I know Baron will also be talking about this in a more elaborate manner. And the other concept is about climate change. So we are having a lot of changes. We are having a lot of disturbing weather conditions. We had a lot of storms. And for example, here in Nairobi, what we saw was the storm, the sewer systems spilling all over the town, all over the city, all over the places. So that is also some of the changes that are happening. Then the other thing was about sizing of our sewer systems. I think Baron is an expert in that one, and will be taking us through the step-by-step ways how we can size our sewer systems and also how we control the slope to ensure that our sewer systems are self-cleaning. The other aspect was, of course, maintenance. So for today, we will not be covering maintenance, but also maintaining our sewer systems is very, very important. And then the other point is about the inverted siphon technology or invention, where you want to get to your sewer system across the river bodies or water bodies. So thank you very much for engaging with us. I'll just go to the chat box and get to see what are we hearing. So for example, Mike Sibanda is saying that the slope of the pipe is crucial for the efficient flow of the solids as well as the wastewater. Also, the advisable velocity of flow recommended is between 1 meters per second, and the depth of the pipes below the road layers, that is where it's crossing roads, is also crucial when you reach below rivers or streams. We use an inverted siphon. So thank you very much. He's talking about the cover, the minimum cover that you need to have on top of your sewer system pipes when they are crossing roadways. Then Sobuza T, this is my guy. I know this guy. So he's saying that one is the proper population projections to optimize and size your sewers appropriately. The other one is taking into account the slope of the major design parameters. That is also agreed and super brilliant there, Sobuza. Then there is a gentleman by the name Redmi 90 who says, when sizing a sewer during the design, we shouldn't only do to cater for the now need, but also to cater for the future needs. So thank you very much. Those are brilliant, brilliant ideas that you've been able to share with us. And I also appreciate the fact that you've been very attentive during our first few minutes. So I'll just introduce myself. I know I just started ranting here, you guys. And Ndinfo Moswe, good to see you. So I'll introduce myself, James Murithi. It's as simple as that. Good to connect with you people. I have been around for quite some time, and I am very happy and I'm very grateful for your support, because when I look at these, so let me just even look at it, my guys. When I look at these faces that I'm seeing here, these are people that have been very supportive in this journey. These are people who have been, how do I say it, who have a great quest to improve their faculties, their skills, and also connect with fellow professionals across the world. So we thank you, myself and the team, we thank you for your support. And we have rebranded the weekly design challenge. So this weekly design challenge is some forum that we created at Ronsab so that we can be able to meet and share knowledge and learn new skills. The design challenge will not only be covering design of roads or sewers, it will cut across all the way to structures and everything. So this one will be happening every Friday, every Friday, same time, 8 p.m. to 10 p.m. We have a lot of things that are packed for you guys. Like today, we are doing Storm Sewer. We'll be doing this also next week. On Friday, also, we'll be having another one on Storm Sewer, if I'm not wrong. And then after that, also we'll bring in some other webinars on road design. We'll bring another design challenges on how to use different softwares. We'll also be bringing other ones on railway design, on structures, on bridges and such. So please make these your home. And these sessions will be exclusively within our community, because we believe that it is important for us to grow ourselves and the people that follow us, the people that we learn with. We feel the responsibility to build you people. We feel the responsibility to learn with you. So all meetings will be shared in our Telegram group. So if you have not joined our Telegram channel, I have been able to share it with you right there. So just click and every information about our design challenges will be there. So we have rebranded it. We want to equip it with the best in the best skills possible. So I have another 2 minutes. That is it. So the community here is for us to grow and learn. It is a community for us to share our ideas. And this is the interesting part. If you there today, you have a topic that you would want us to cover, you have space to share it with us. You can share it in the chat box right away. You can be able to share it. You can be able to DM me. You can be in the captains, and we will be able to plan it as well. If also you want to be a guest in this one, this is community for us. We have just created it, and it is for us, and it is for you. So if you wanted to share something also, you can be able to join us and get to we can get to feature you. We are open to learning and innovation. All right. So allow me to introduce our today's guest speaker. I know Baron Sirent is already here with us. So Baron Sirent, when I'm told to describe, I really have a funny ways of describing the people I know. So for me, we call this gentleman at Roadsub, we call him Mr. Storm. I don't know why, but we just decided to call him Mr. Storm. We have some really weird nicknames at Roadsub. So he is from South Africa. He is a specialty he's a civil engineer, specializing in sewer design, sewer systems or utility design and all of that. He has been with us for the last almost 1 year now. And one thing that I have admired about this gentleman is his resourcefulness, his kindness, and also his ability to teach in a very empathetic way and in a very understanding way. So these are one of the things that we enjoy about this gentleman. He is very patient with us, and I know he has prepared a very good session for us. So allow me, ladies and gentlemen, to introduce Baron Sirent so that he can take us through what he has for us today. So Baron, are you there, gentlemen? Are you ready?
Yes, engineer, I'm here.
All right, take it away.
Yeah, good evening, guys. Good evening. Thank you so much, Engineer James, for that warm welcome. I already feel special. Thank you so much. I really want to appreciate you guys for showing up and supporting our brand, Roadsub. It's gonna be awesome. So I just want to reiterate one thing that Engineer James said about the design challenges that we're gonna be having every Friday. This is the place that you need to be. So please just make sure that you mark it in your calendars, because every Friday, there's going to be something new for you to learn. There's going to be something great for you to learn. There's a saying that we always like to, sort of like our poster saying or our mantra at Roadsub. We always like to say, the world is too complicated for you to strike it alone. You need a tribe. You need a team. So this is exactly what we're trying to achieve at Roadsub, to build a community of engineers that can help each other thrive in our profession. You know, you might be practicing civil engineering in Barbados. I hope I pronounced that well, Justin. And you face some difficulties. You might meet someone in this group, Sopuza, Lerato, you get to chat with people from different countries and share knowledge and impart wisdom. So this is exactly what we're trying to achieve. Yeah, I've been part of Roadsub for some time now, and I've met some amazing people. I have friends. I met friends here that we were actually doing civil engineering together. We're doing some amazing cool projects together. So I cannot overemphasize the importance of community, building a community and being intentional towards that regard. So yeah, I'd really like to encourage you guys to always show up on Fridays. This is gonna be awesome. But anyway, for today, we're gonna be talking about the fundamentals of sewer design, right? Your sanitary sewer design. What is it? What is it all about? What happens there? Like, okay, fine, when you flush your toilet, what happens? Does your stuff magically disappears? Okay, when you take a shower. Or, I like this one, when you accidentally drop your mother's spoons down the drain and you just pour water and you keep quiet and you don't confess your sins. What happens to those spoons or those pebbles or that sand that you use to scrub your pots that you just throw down the drain? What happens to it? Does it just disappear? So we need to discuss these things and find out what really happens, because as a civil engineer, like Engineer James said, public health is our responsibility. We not only design structures that are cool or that look really cool, beautiful, or anything. Yes, aesthetics is important, but also safety is also important. You'd realize that even in structures, when you design anything that you design in civil engineering, it has to have a safety aspect to it, right? Because lives depend on it, right? We always like to say this at school. I remember when I was in college, we used to argue with the medicine guys. They would say the doctors are the most important people in society, and would rebuff their statement and say, no, it's the engineers. It's because when an engineer makes a mistake, thousands of people die. But when a doctor makes a mistake, it's one person at a time dies. I'm not trying to say lives are not important, but I'm trying to paint a picture of how important your decisions are. So if ever you make a mistakes in your designs, be it you're designing a road, that particular road will claim lives. If you're designing a structure, if it fails, you know that people are going to die. So if you're designing your sewer systems and it fails, you know that the public health of people is compromised. Cholera, all these waterborne diseases will just strike communities and people will lose their lives. So it's very important for us to approach our engineering disciplines with that mentality to say, listen, lives are dependent on this. I'm not just designing something for the sake of designing it, but safety is also part of your thinking process. Please do forgive me. I'll be muting from time to time. I have a terrible cold or flu, so yeah, I'm under the weather a little bit, so I do apologize in advance for that. So allow me to share my screen, you guys, so that I can just get straight into what we are discussing today. All right. So I'll be sharing my screen just now. There you go. Share sound. All right. Please confirm if you can see my screen. Just type a 1 in the chat box. Okay, let me check. Awesome stuff. Awesome. Thank you. Nonkululeko. I hope I pronounced that well. Yes, I'm really practicing. All right. So guys, today we're talking about the fundamentals of sewer design, right? Your sanitary sewer. So I'll just basically start from the basics, right? I'll just assume that no one knows what we are talking about. And rest assured, this session is being recorded. So because you're part of our community, you would have access to it so that you can rewatch it and refer to it, right? So what is your sewer system? As you can see here, apologies, this screen is a bit blurry. I don't know what's happening with my resolution on my computer. It's taking time to load, but I'm sure you can see what's happening, right? So as you can see, these are houses that you can see here. I don't know if that's a house or that's a church. And you can see those are roads, those are your street poles. And underneath these structures that you're seeing, they're actually underneath because we don't see them. I don't know if there's anyone who have seen a sewer pipe before or a manhole. We've never seen that. So if we're talking about the sanitary sewer design, I want us first of all to realize that these are structures that we seldomly see in our environment. We don't even care. We don't see them. We don't see the pipes because they're all underground, right? But they're actually working and they're serving their purpose. We don't need to see them. All right. So contents to be covered in this webinar, we're just going to be talking about the fundamentals of sewer design. We're going to talk about sewer layout in Civil 3D. So yeah, you're going to learn a little bit about Civil 3D here because we use Civil 3D here in Rhodes Hub. It's a very cool tool. I'm also going to talk about hydraulic modeling there, right? I just want to mention something really cool. When it comes to softwares, you guys, there are a number of softwares that are out there in the market. I was talking to this lady engineer today, and they were strongly advocating that I start using IDAS or Civil Designer. I'm sure you guys, some of you guys know about it. It's a very cool software. You can pretty much do everything about it. But what I want to mention to you guys is that the software does not do the design. You do the design. Civil 3D does not design. Civil Designer does not design. IDAS does not design. You are the one that designs the source system. The software merely helps you to do it in an efficient manner. So the software is a tool. It's not the one that designs. So I want us to have that thought in mind so that you run away from being just a chimp who's just clicking on the computer. You are the ones that feed the information into the software. So you need to feed it the right information. We usually, my doctor at school, Dr. Chinyama used to say garbage in, garbage out. So if you feed your software garbage, it will just give you garbage as a result. So you need to understand that it's not the software that designs. So I always get this question all the time. Okay, which one is the best software to do this? Which one is the best software to do that? And then my answer is the software is not part of the conversation. It's understanding the fundamentals, understanding the principles behind sanitary sewer design, or understanding the principles designing your road, or understanding the principles designing your structure. That's engineering, and making timely decision and making decisions based on those principles. That's what we call engineering. So engineering is not just using softwares. So just to answer also that question, I like Civil 3D, fortunately, for obvious reasons. Civil 3D communicates well with other BIM software such as your Navisworks and your Revit. So I like it for that reason. You can use IDEAS, you can use Civil Design. It's still fine. We can still probably get the same results, but I genuinely prefer Civil 3D. It's more of a personal preference. So in this particular design, or in this particular webinar, we're going to be looking in Civil 3D. That's what I'm going to be discussing about. I do not have knowledge about IDAS or Civil Design, and I do not intend to learn it anyway. So I hope you got understand that Civil 3D. Therefore, I want us to talk about the definition of the terms, right? So as you can see, you guys, to the right, this image here, that you have here. As you can see, I have got a number of pipes there that you can see. There's roof drain. This is the house here. Unfortunately, it's been cut, but it's not important. So we are seeing a number of pipes that are flowing from the house, right? I'm seeing this pipe that's connecting to this pipe, and I'm also seeing this pipe that's written sanitary sewer lateral that's connecting to this pipe, and I'm seeing this thing that's written catch basin. So one thing that you guys have to understand that there is what we call sanitary sewer and storm sewer. Those are two different things, right? As you can see from the words, there's a storm sewer. The storm sewer, it collects your storm water, right? This is the water due to the rainfall, right? The water that when it rains, water that's collected by your catch basins, water that collect on your side drains of your roads is collected by your storm sewers. Even when your gutters for your house it has got down pipes that then pour into, side drains, then that pour into these pipes that pour into your storm sewers. So you have got storm sewers, and then you've got sanitary sewers. Today we're talking about sanitary sewers, the design of sanitary sewers. Storm sewers is a separate design altogether that has got its own principles. Hopefully we're going to talk about it in the near future in our design challenges. So just stay put on that. So yeah, I'm not going to touch about this, but one thing that I want you guys to know is that in our recent what can I say, urban councils, most of the urban councils, they separate these two. There's a separation between your sanitary system and your storm sewer system, right? It's called a separate system, right? There are some, but the combined systems, they were like used back in the day, but they are now updated. We now use separate systems, which means that if ever you try to divert your storm water into your sanitary sewer, you will be found in offense according to the local municipal bylaws. It's a criminal offense. you can be prosecuted and go to jail. So if ever you design your storm sewer, never divert it if ever you've gotten access to a manhole to say, oh, let's just pour it into a sanitary sewer system. It's a crime. Please do not do that, or else you'll be in trouble. So according to the recent bylaws, most municipalities in the world, they use a separate system. So you've got your storm sewer, then you've got your sanitary sewer. So Tina, we're going to talk about our sanitary sewer system. Now, when we're talking about a sanitary sewer system, first of all, what is sewage? Let's just start from there. Someone might be asking myself, what is sewage? I know you know what sewage is, but what is it, you know? So luckily, I have got a definition for you guys. Sewage is the wastewater. Okay, please mark these terms. Sewage is the wastewater and excrement conveyed in sewers, right? So first of all, you need to understand that your sewage is wastewater. It's wastewater, right? And also excrement that is conveyed in sewers, right? So your sewage can be produced. There is what we call domestic sewage, right? This is the sewage that comes from your houses, you guys, right? The sewage that when you take a shower, you flush your toilet, you know, you do your laundry, you wash your dishes, all that water that you no longer use after you use cleaning your house, doing whatever you clean yourself, all that water that you guys produce in the house is called your domestic sewer, right? Then we've got industrial sewage, right? So this is usually sewage that is produced in industrial areas after industrial processes and manufacturing processes. There is usually wastewater that is produced whenever industrialization takes place in terms of your manufacturing. Usually this water is contaminated with heavy metals and solids and stuff. So we also need to think about those things. Suppose you're designing a sewer system that is also catering for an industrial area. So that's a different topic altogether that has got its own guidelines and bylaws, and it's a whole lot of literature that we cannot cover in this webinar, but just know about it. So we've got our industrial sewage. Then we've got our commercial sewage. These are commercial buildings that also produce sewage. So we're talking about your office work, office spaces. We're talking about your schools, all the institutions, right? Commercial buildings. So that's also commercial sewage. But one thing you would notice that all this sewage has got one thing in common, right? It has got water or fluids, right? So this sewage consists of usually two things, which is your fluids and then your solids, right? If you notice that. So your fluids are called your silage. It's called silage. So the fluid part of the sewage of the wastewater is called silage. Then the solid is called sludge, right? So your sludge could be anything from human excrement to, you know, how people when they do dishes, they just throw pap down the drain, or your leftover food, you just throw everything down the drain. People do abuse our sewer systems. I get very emotional if I see people do that because they don't understand how I feel. So people just flush all kinds of solids down the drain and they hope magically it flows away. So your solids make up what we call the sludge. Then the fluid part of the sewage is called the silage. So I just want you to take note of these terms. Please make sure that you've got somewhere where you are taking down your notes. Okay, just write down, scribble down some notes because I'm going to be dropping some pointers that might not be part of my notes as I present. Then we have got our sewerage, right? Remember, we've got sewage, then we've got sewerage with an R, right? RA. Like what's your sewerage, you guys? Sewerage refers to the infrastructure that collects, right, transports, treats, and disposes sewage to your wastewater and your excrement. So remember, your sewerage is the infrastructure, right, that collects, transports, treats, and disposes, right? So infrastructure, I'm talking about your pipes, right? So what is the infrastructure that we're talking about? We're talking about your pipes, these ones, right? This one, that's your sewer. Then we're talking about what we call manholes, your access manholes, right? So in this particular webinar, because we only have like 1 hour and 10 minutes, I'm not going to talk about the treatment and the disposal. I'm simply going to talk about the transportation part, the collection and the transportation part, right? Those are the two that I want to delve into detail today. So manholes, right, is this structure that you guys are seeing here. Unfortunately, I did not actually have a better view of it, but you'll see as we proceed. This is the structure that we call, this is a manhole. It's called an access manhole, right? I'm sure you've seen this before. It's also this structure. Yeah, this is the structure. If you can see it very well, it's also this structure here. That's your manhole there. That's your manhole. That's your manhole. That's your manhole. And these are your pipes. You see, I'm sure you guys know pipes, right? So what is a manhole? Manhole are access points in a sewer system that allow for inspection, maintenance, cleaning of sewer pipes, right? So manhole are access points because we need to have access into these sewer systems. Somebody asked a question about maintenance. Unfortunately, we're not going to talk about maintenance today, but it's also a great topic to touch on. So your manholes, they provide us with that access so that we can inspect, maintain, and clean. Just take note of the cleaning part, right? Also, your manholes are always provided whenever there is a change in direction of your pipes. Also, guys, you know, take note of that. I did not include that in my notes, like I said, but it's just something that pops in my head. So whenever we're designing our sanitary sewers, you can see we have a pipe that's going this way. Now, I want to change direction and come this way. I have to provide a manhole. So whenever there's a change in direction between pipes, right, they should be provided a manhole. Whenever there are two or more pipes that meet, we also need to provide a manhole. Whenever there is a change in diameter in the pipe system of your sanitary sewer, we also need to provide a manhole. So what I mean is, let's say you're moving from a pipe diameter of 160 millimeters and we are going to a pipe diameter. Let me use a different marker there. Let's try red, right? Good. So I'm going to a diameter of, let's say 200. I'm coming from 160 millimeter diameter. So here I have to provide a manhole to enable that transition. So whenever we are moving from one diameter to another, we provide a manhole. Whenever we're changing direction, we provide a manhole. Whenever there are two or more pipes meeting, we provide a manhole. So you need to know, guys, manhole are your access points. Manhole, they provide for inspection. They also help for maintenance, right? Right. Great stuff. Right. Then we have got our pipes in our sewer system. Pipes in sewer systems, they then convey this sewage from your homes, from your businesses to industries, right? So they now convey this this sewer that has been collected from the houses, right, in the pipes, right? Great stuff. Okay, so now we're just gonna go to the layout in Civil 3D. This is where it gets interesting. This is why I love Civil 3D, you guys. Civil 3D enables me to do what I call surface analysis, right? I'm sure when you watch that video that we spoke about, this guy spoke about slope, and I'm sure a great number of you guys were saying slope affects our sewer system, how it functions. It affects this component that we call the cleansing velocity. Always take note of that word. So slope, so which means if I'm thinking about slopes, which means I need to know how my surface is behaving, like the terrain. So I need to do my surface analysis, right? So that I can design my sewer in line of the surface, right? What does that mean? Right. I use what I call use a quick profile tool to map out the direction of flow. So I need to understand where my sewer is going. So Civil 3D enables me to do my surface analysis. It also enables me to lay out my slopes. So I'm going to lay out my sewer in the direction of my slope, right? I don't oppose the direction because remember, sewer flows under gravity. Okay, this is important. Please take note of this. This is a gravity pipe type of system. It flows under gravity. It's not a pressure pipe system. We're not going to introduce a pipe, a pump in any of the system, unless if we want to do a pipe mains where we're now lifting the sewer, probably we're pumping it to a treatment plant. But if it's just a regular sewer system that's flowing or that's collecting sewer in houses, we do not need pumps. In fact, pumps are expensive. Yes, there are instances that we use pumps, but sewer systems, they are gravity pipe systems. So they are essentially functioning under gravity. So gravity has got what slope? You guys should know this, right? Acceleration due to gravity. So suppose my slope, let me give you just a supposition, just a scenario here, right? Blah, blah, blah. Which color do I like? Yellow. Yellow is a happy color. Let's use yellow, right? Suppose my slope, this is my natural ground slope that's going that way, you guys, right? This is my natural ground slope. And the most sensible thing, if I'm laying my sewer line, I have to be in line with the slope. I can't lay my sewer line going this way, you guys, because I'm opposing the slope. And remember, your sewer line has to be at a certain slope as well. So we're saying there should be a slope difference here, right? There should be a change in that angle theta there so that your sewer can be able to flow by gravity. But if I oppose my sewer like this, it simply means that I'm going to have to trench at very deep levels so that I can be able to lay my pipe. This is very, very expensive. It's a very expensive endeavor. I'm sure when you guys also watched, Grady mentioned something about when we lay out sewers, we do it right and we do it once. Because just the exercise of laying out of sewers, it's a very costly exercise. It's expensive. So we need to make sure that we lay our sewers in line with our slope. So if this yellow line is representing my natural ground floor, right? This is the natural terrain. So which means the most sensible thing for me to do is to lay my sewer in line with my slopes, right? It will probably go in line with my slopes. Also, there's my manholes. Probably put another manhole there, or probably put another manhole there. So it only makes sense that your sewer has to be laid in line with your slope, right? This is to ensure that we take advantage of the slope so that we can increase the cleansing velocity. Also, we need to lessen the amount of earthworks. Please take note of that we are going to generate by excavating so that we can lay down our pipes. Take note of that. So I do all that in Civil 3D. So one of the ways that I do that is after I do or create my surface, which all is done in Civil 3D, I get my survey points, create surface, do your surface analysis. We're not going to touch on that. We're going to touch on that some other time. Your surface analysis in depth. After I do my surface analysis, I do what I call the quick profile to map out my flow. Just take note of this because I'm going to just show you an example later in this webinar. So as you can see here, you guys, I drew my lines. As you can see there, sorry about that. As you can see here, I drew this red polyline here, right? This is showing the direction of sewer with an arrow. Someone might be asking themselves, what's happening here? These are stands. So this is a low-income housing scheme, right? So these are stands. As you can see, these are residential stands: 191, 27, 216, 215, 214, then 192, 193. It's going that way. And these are your roads, these ones. These are access roads. So as you can see, in your low income housing, your stands or residential stands, they are designed in blocks, which means they're designed back to each other. I'm sure if you've ever stayed in a high density suburb, you understand what I'm talking about, or even in a median income density. There is a part where you share a perimeter wall with your opposing neighbor. So you actually share this perimeter wall. So how we lay our sewers is we lay our sewers in between those stands, right? Because it's cheaper that way. If we lay our sewer line in between those stands, that way enables us to service these batch of stanzas and these batch of stands at the same time. It's much more economic for us to do it this way, rather than someone would say, okay, fine, Byron, what if I lay my sewer in front of my housing stands? What if I lay my sewer in front of my housing stands? Suppose you want to lay your sewer like that. It's still fine, but you are only servicing only these stands. You are not servicing these stands, you understand? So you need to also put another sewer line this side to service those stands. But you'd realize that you are now, your project now becomes very expensive, because rather than just us laying one common pipe here that will service both those stands, the stands on this side and stands on this side, you are doing two stands. You know what I mean? You are doing two separate sewer lines. And laying sewer lines is very expensive. Like, you need to lay out your manholes. Your manholes are made of what we call precast concrete. They're expensive. Your pipes are expensive. Trenching the pipes is expensive. Like, doing the pipe bedding is expensive. So it's an expensive process. So rather than we just have one common pipe there that we lay in between the blocks of those stands. So that's a common way. So I'm not going to get in depth about that and about the bylaws and everything. I'm just going to briefly brush through it. So those are your stands, as you guys can see, right? In case you're asking yourself, what is this dude talking about, right? So I've got my sewer line and I've got my direction, right? So according to my direction, I did a quick profile and I know that my slope is sloping towards this way. So I now just draw a polyline right there that is going to guide where I'm going to lay sewer line, right? So just take note of that. Just take note of that, right? So that's what I use Civil 3D for, right? So I do Civil 3D for just understanding how my slope behaves so that I know when I'm now starting to lay out my sewer line, I've got an idea of which direction I'm taking so that I can map up what we call the outflow sewer, right? That is very important. So remember, we have to always design in line with the natural ground, right? Take note of that. Now, we're also going to talk about the hydraulic design, you guys. This is very important, the hydraulic design. If you also watch the video, we also mentioned something about how much to expect when designing a sewer system, because we need to ascertain, or we need to come up with a figure. How much are these people, how much sewer is it going to be generated by this place that I want to design? Because you need to have a figure, you need to have a design flow so that you can be able to appropriately size your sewers, right? Because if you don't have a design flow, you will probably do guesswork. And if you do guesswork, two things are bound to happen. It's either you're going to under design your system, right, which is going to cause problems, catastrophic problems, because your sewer is going to overflow all the time. You're going to have outflowing manholes. It's going to be a nuisance. Sewage is smelly, right? We all know that. It's not something that's very, pleasant to see. That's why these pipes are dug underground. We do not want to see it, right? It's socially disruptive, right? So if you under design your systems, what happens is that they will overflow. Then sewer is spilling all over the places, right? Risk of it contaminating your drinking water. We do not want that. Then if you over design, right, now that's another problem. If you over design, which means your sewers become unnecessarily large and they also become unnecessarily expensive. So this is what you also need to understand. Like, a modern engineer does not only design for safety, but he has got this thing that we call cost in mind, right? Me and you can design a sewer system, and yours can work, mine can work, but the efficiency of that system also comes down to the cost, you guys, because yeah, it costs money to build projects. This is also another part of being an engineer, understanding the cost implication of your decisions, because everything needs money for us to implement it, right? So this is where the hydraulic design comes in, so that we can we can come up with an informed decision. We just don't need to guess, right? So we're gonna do a hydraulic design, right? So part of the hydraulic design is this thing called a cleansing velocity, this phenomenon called the cleansing velocity, right? So I'm going to attempt to define your cleansing velocity, right? Your cleansing velocity in sewer system refers to the minimum, please take note of that, refers to the minimum required velocity, minimum flow velocity required to prevent deposits of solids and ensure self-cleansing capability of sewer pipes. I'll repeat and I'll explain. I'll break it down for you. Cleansing velocity in sewer systems refers to minimum flow velocity required to prevent deposition of solids and ensure self-cleansing capability of sewer system. So what we are saying, you guys, is that you have a sewer system, right? That you have. Okay, there you go. We're still using blue. So I have my sewer system, right? There you go. It's just a pipe. I've got my main hole there, right? And then we said we are going to have our natural ground level like that. Okay, we're good. So what happens is that I'm going to flush, probably I'm going to take a shower, right? Then I produce some sewer that will start flowing in here, right? Then my neighbor is doing dishes. Then they accidentally drop a spoon into their sink, right? They just ignore it and they pour down water down there. Now that's a large object. It will probably settle there because it does not have enough energy to just flow down the drain, right? Then someone has got leftovers of pasta and lasagna that they made last night, and they don't want to throw it into a compost or something, or throw it in a bin or something. They're like, I'm too lazy to go outside. Let me just flush it down the drain. Let me just throw it down the sink. They do that. So I've got my spoons there. Someone just scoured their pots using sand, and then they rinse everything and they just, everything. I've got sand there, I've got pasta and lasagna there. So what happens now is that if you've got a flatter pipe, right, which means your flatter pipe is close to resembling a flat line like that, right? What happens is that these sediments, they have a tendency of settling in your sewer system, because if we're saying we have got a flatter pipe, it reduces your velocity of the pipe. Then when it reduces your velocity of the pipe, which means the particles don't have enough energy to move themselves down the drain by the effect of gravity. So they've got a tendency of settling. They deposit on this pipe here. So what happens that as they continue to deposit and build up, it will result in a blockage. And then when it results in a blockage, when you now flush, this guy flushes, now the water can't now what pass through the pipe, it will do what we call a backflow. That's the worst thing that can happen. Imagine you're taking a shower and then you see poop start coming out of in your bathroom. That's a nightmare, right? I'm sure you cannot even think about it. That's a nightmare. I've seen it happen. It's called a backflow effect. So what happens is that now if your sewer system clogs, right, there's gonna be backflow. All that stuff that you guys flush down, it is just start coming and the water is not going. Or I'm sure you guys have had a blockage in your house and you to call a plumber and they bring a rotting eye and then they start doing some funny jerking movements in your pipes. We're going to talk about that. So they're just trying to clean these blockages. So how then do we avoid this situation? We avoid this situation by designing our sewers in such a way that they can clean themselves. Number one, nobody has the time to always go underneath into the sewer system and inspecting what's happening. So we need to design our sewer system in an efficient manner so that it can clean itself. By cleaning itself, it means that it has got the capability of obtaining velocity so that it can wash away all these sediments so that we don't have anything that's settling in the sewer system. So such that if I flush down a spoon, I'm not saying do it, please don't do it. Please don't. Spoons, no. Right? I'm just saying God forbid, if it happens, somebody flushes down a spoon, somebody just shoves down their lasagna that they left last night. We're saying your sewer system must have an ability to cleanse itself. So it must have the energy to push all those sediments down so that we do not have blockages. All right, so that's cleansing velocity right there. So it's the minimum flow velocity that is required to prevent, you guys, to prevent the deposition of solids and ensure self-cleansing capabilities of sewer pipes, right? So maintaining an adequate cleansing velocity is crucial for efficient functioning and longevity of the sewer system. All right, so I'm happy with that. I hope you guys got that. So now we've got factors affecting cleansing velocity. We talked about your slope, right? Take note of these, you guys, because these are going to come in handy when we start talking about the hydraulic design, the meaty part of this whole process. So we've got our pipe slope, we've got our pipe diameter, right? We've got our flow rates. So this is the capacity, like how much sewer is being generated. Then we've got the roughness of the pipe. Though this one is redundant because mostly we're going to be installing new pipes, right? So we usually just assume a roughness of about 100, depending on what formula you're using. If you're using the Manning's equation, we have got a roughness that we assume. So this one is quite redundant, but it does have got a little bit of effect to it. But the ones that I really want you guys to think about is your pipe slope, pipe diameter, and flow rates. All right, so that's our hydraulic design there. Now comes to the formula, you guys. Yeah, you are not going to run away from formulas. We are always going to have to calculate. When we're in roads, you still remember when we're calculating the minimum radius and stuff, we had formulas, super elevation with formulas. We're always going to use formulas. We're engineers. You can't run away from it, right? So as you can see, you guys, there's this formula called the Cobb-White formula. It was invented by this guy called Kubrick. He's quite cool. But anyway, we're not talking about that. We're talking about the formula, right? This is the formula that we use, the Kubrick-White, right? I'm going to be diving deep and describing everything in that. Then there is the Manning's formula, you guys. Then there is the Manning's formula. So this is what actually usually happens. In countries like Canada, the USA, usually the Western countries, they prefer using the Manning's equations, most of them. I've worked with some guys from Namibia before. There's some guys that prefer using the Manning's equation also for doing their calculating the cleansing velocity. As you can see, V is the subject of the formula, right? That's the cleansing velocity. So this formula is calculating your cleansing velocity. V is the cleansing velocity, in case you're asking or you're wondering. So when we're talking about this formula, we're using the formula so that we can calculate the minimum required cleansing velocity, right? Using these parameters that you see. Then the cube required is mostly used in the sub-Saharan region countries, but most African countries, they use the cube required. So there is no harm really. You can use the cube required equation, you can use the Manning's equation. It's up to you, right? It's up to you which one you like to use. I personally prefer the cube required, and I've got my own reasons why I prefer the cube required. But some guys use the Manning's equation. You might be there, you use the Scooby equation, there is the Strickler equation. There are a number of equations out there that you can use. But they all give you the same things with what parameters do you have. But for start the universal equation, because it applies everywhere, right? It applies everywhere. It's the most used equation in the world when it comes to sanitary sewer system design. So for the sake of uniformity and conformity, we are going to be using the cube required equation, you guys. So I'm going to explain these equations for you. I've got less than 50 minutes to pull this off. So let me try and move a bit faster. Right. So this is our cleansing velocity, right? V, that's your cleansing velocity. Of course, that's 2. That's 2 right there. That small g is your acceleration due to gravity. It's g, 9.81 meter per square second, right? D is the diameter of the sewer and pipe. It's always given in m meters. Then S is your slope, right? It's given in, S is dimensionless, so that you know. So that's your D diameter, S is your slope. Then K, that's the roughness of the pipe. So if you're using cube required, you are given the roughness of the pipe that you're supposed to use, right? Then we come to your D, sorry, we come to your D, that's our diameter. Then we come to that V that you see, that's called the kinematic viscosity. That value also given there. It usually ranges from 1.2 to 1.4 times 10 to the power of minus 4. So you're given that value there. Then G again, that's our gravity. Then D, that's the diameter of the pipe. Then S, that's the slope. So yeah, we're not going to talk about how this was derived, you guys. If you're like me, I'm very curious because I like to know what I'm using. So we're not going to talk about how it was derived, but you just need to know how to use it and all the parameters in that equation. Then we come to our Manning's equation, right? Then we've got V, we've got our N, which is the Manning's coefficient. We've got the hydraulic radius. This is why I always run away from the Manning's equation. I'll explain this. It's the issue of the hydraulic radius. It gives me so much stress. Hydraulic radius is called the weighted perimeter over which a circular pipe is flowing full, right? It's a whole different calculation there. Then we've got our slope. So if people usually choose the Manning's equation because it looks simple, right? It has got like what? 2 parameters in it compared to this cube required that looks scary, right? But here's why I like to use the cube required versus the Manning's equation, right? The cube required, also known as the universal, in quotes, mark that, is widely used for the following reasons. Or let me say, I use it for the reasons I'm going to state here, right? Number one, the formula has got low sensitivity to inputs compared to other formulae, right? For example, if I change n in the Manning's equation, let's say from 0,011 to 0,015, which is like 1.34 times, the increase in velocity or the decrease in velocity is 27%, right? The 27 drop in velocity. While in Colebrook-White formula, if I change from 0,6 to 6, which is like what, 10 times, right? The increase, it only results in 19% drop in velocity. So you can see in terms of stability, my Colebrook-White is quite stable. And also, you guys need to know that from the foregoing, it can be concluded that the results from the Colebrook-White formula are stable and do not rely heavily on the judgment, opinion, and experience of the designer in selecting the inputs, right? So for these reasons, we're going to be using the Colebrook-White formula going forward, right? I'm going to touch on an example right now, right? So I hope you guys were taking notes of everything that I was talking about, because now we are going to see how we apply it. Now is the culmination of this entire thing, right? So just take note of this, because usually the weighted perimeter, it requires someone who's experienced, because there are a number of engineering judgments that you need to make there. But for the code required, it does not rely on your judgment. It does not require your opinion. We are just taking the values as they are, plugging in them, and then getting your cleansing velocity. All right. So before we jump into the example, I'm just going to check the chat box and see if there are any questions that need to be answered. All right. I believe you can. Okay. Someone was answering something. Why can we not lay sewer line? Why can not we lay sewer line? Okay. I'm not getting that. Maybe he's trying to say along the roadway. Okay. Yeah. Uh, it does. It can be laid along the roadway. It's a different conversation altogether, because when I think we spoke about this some time back when we were talking about the integration of your road design and your storm sewers, right? But yeah, it's a different conversation altogether. So for maintenance reasons, I believe, all right, I believe this one was trying to answer that question. All right. Okay, so fine. Also, please just thank you, Katimo, for that. That's a good answer. That's a good answer. I'm not gonna go through that. So if you guys got questions, please just drop them in the chat box. There's Katimo, there's Felix. They know this stuff. They will help you out. All right, so that we don't disrupt the flow of the session. I have 45 minutes to try and bring this thing to a landing. All right. So I've got an example, you guys, that I want you guys to really pay attention to show you how do I bring in my hydraulic design, and how do I bring in my my civil 3D aspect. So whenever you're designing your sewer system, you start with what we call a preliminary design, right? You start with the prelim design, right? So you start by actually laying out the sewer, right? You start by laying out the sewer, you start by proposing the pipes, you start by proposing the slope, right? So this is what I want us to do. I'm going to take you guys to Civil 3D right now. Just hang on. Right. Okay. My Civil 3D is acting up. You guys just forgive me over that. Let's give it a moment. Anyway, right. So this is a mid-block section that I was talking about, right? So you are given this stance. You're given this stance here that you guys are seeing here, right? I'm not going to do surface analysis. The surface was already created and everything. So one thing that I wanted to show you guys is I want to figure out where is my sewer going. So quickly I do what I call the quick profile tool. So I go to my polyline. First of all, I create a layer for the sanitary sewer. As you can see, I created a layer there. More on that. Oh snap. Unfortunately, my sewer. Okay, that's disaster. Just give me a moment. I see for 3D just crashed. Just a moment, you guys, as I sort it out. Apologies for that. All right. So while I wait for the Civil 3D to come up, I think it's just gonna take 2 minutes. If you got questions, please just drop them in the chat box so that I take this time to answer them, so that we don't kill the momentum. If you've got some questions, you can just drop them in the chat box, and then we sort them out. All right, I'll give you the benefit of the doubt. I'm sure someone is typing. All right. So I was saying that, so when you're designing your source system, you start with the preliminary design. So the preliminary design is done in Civil 3D. So you actually lay out your pipe. So after you've laid out your pipe, then you take those parameters, then you do your hydraulic design to check if your sewer is sufficient, or if your sewer is functioning in an optimum way, right? Okay. So someone is saying, how do you generate the surface? How do you generate the surface? So the surface, this is how you generate it. There are a number of ways you do it. You're usually given these points by your surveying team. So the surveyor will go on site and you take your surveying points. Then after he takes those surveying points, you're given those surveying points, then you import them into Civil 3D. You apply your description keys, then you create a surface, right, from the points that you get from your surveyor. So that's how you actually create and model these surfaces. All right. Okay, stuff. All right. Kindly share your screen. Yes. I'm just waiting for my Civil 3D to pull up because I want to show you guys a preliminary design. Part of what I wanted to do today is to show you how to use Civil 3D to actually lay down the pipe. All right. So no, the screen is coming. Just be patient with me. There you go. Aha, we are almost there. All right. So someone is saying, can you share the files? Unfortunately, I cannot share the files with you. It's intellectual property. However, don't despair. If you want to practice, I can make a plan for you. I'll find something for you to practice with. So for this particular example that I'm sharing with you, I cannot share the files with you. All right. Let's keep the questions coming, guys, so that we don't stop the momentum. Anyone else? All right. So what I'm going to do, while we wait for our Civil 3D to start, I want us to start on our hydraulic design, right? Right. So we're gonna do our hydraulic design. So allow me to share my screen now. Awesome stuff. There you go. Okay, I'm sharing my screen. Just a moment. There you go. Right. Awesome. Right. Share your screen. All right. Ignore. Awesome stuff. Right. Please confirm if you can see my screen. Confirm if you can see my screen. Confirm if you can see my screen. Just drop a 1. Awesome stuff. Let me check. Thank you. Thank you for that. Anyway, sorry for that, guys. I'll make up for that 10 minutes. All right. So I was saying, we start with our preliminary design, right? So first of all, I need to understand where is my sewer going, because I'm just seeing a bunch of stands, right, that are designed in a block way, and I'm seeing contour lines. If you know how to read your contour lines, you should be able to know where the terrain is going, right? So there's one way of doing that. Some people can read their contour lines. I do not want to do that. I can, but I've got a much more easier way that I like to use, which is the quick profile tool. So you just go and you click your polyline. This is an AutoCAD 2D tool. So you click there, right? So I'm just drawing a polyline. I just want to see. So remember, I want you guys to note something. Check where I started, right? I started from this side and I'm going this side. So I'm starting from right, I'm going to left, right? So check note of the direction. Let me turn my object snap. Then I click there. I'm going to terminate my line there, right? Okay. There you go, enter, right? So I want to check the terrain of this thing, right? So you can click on that polyline, right? Click on it, right click, go to quick profile, right? After you do quick profile, you select that, that's the style. I want to talk about that later. Then you click anyway. Awesome stuff. So what does this look, you guys, look. This is the quick profile of that line. So this line, this green line is showing the natural ground level. Simply to say that my ground is sloping from this way. So I'm moving from left to right. So it's sloping from this way. So automatically, if I do this, intuitively, I know as a designer, my pipe is going to be following what? This slope, right? So now, okay, fine, I'm winning, right? I smile a little bit. Okay, fine. So let's see. Let's try and do a quick profile for these ones as well. So I draw my line there, right? Just to see what's happening, you guys. Then I click on it again, right? Just click on it, right click, then you go to quick profile, right? Then you select the surface. That's the name of the surface. It's just named contour. Then you can click anywhere, right? Oh, great stuff. As you can see again, that's my quick profile. So this is showing the direction of what? Of the terrain, of the natural ground. So which means if ever I'm going to lay my sewer, I'm going to lay my sewer according to that line, right? So what you can also do is I can just put what? My direction. It does not need to be a perfect arrow, but automatically I now know my direction right there. One thing that I also want you guys to know is that this line is dynamic, right? So watch something here. Let me just try and do this for you. Okay, it's not gonna move. If I move this thing, if I move this line here, let's say I move this line and I do this, watch, this will change, right? I move this line, I put it there. You see, it changes, meaning to say it's dynamic. Whenever I change this line, it also changes the quick profile too. So this also helps me. Civil 3D is very cool in that sense, because if it's dynamic, I can be able to make changes until I obtain a profile that is favorable to my design, right? That is following the natural ground level, right? So now that I've done that, now I want to lay my pipe network, you guys. So what you do is you go to your prospector, right? There's two ways of doing this. You go to what? There's pipe networks here. You can actually literally create a pipe network here, right? Or you can go to this tab here. You go to create design. You see, you guys, there's parcels, alignment, intersections. We go here to pipe network. You click that drop down. There's pipe network creation tools, create pipe network from object, pressure pipe network creation tools, create pressure network from object, etc., etc. We're going to use this one. We're not going to talk about all of these, but in the future we will. So for now, we're just going to use pipe network creation tools, right? I click that. What is the network? So let me just say sanitary webinar, right? Web, that's the name of that source system, right? Then there comes this part where it's called part list. This is important, you guys. This is important. Please refer to the videos that we have made regarding this. If you check our database on LinkedIn, we spoke about these things. So you go to your part list, I select sanitary sewer. Then the surface, I have to select the surface because I'm designing my sewer system relative to a surface. So the surface of that area is called contour. I'm not going to touch about these, you guys, because we're rushing. Then structure label, I'm probably going to use this structure label set. These are styles that are already preset, right? For the sake of this course, I'm not going to be talking about that. Then I click OK. After I click OK, there's going to be a toolbox that shows up. This one, you guys. There's a toolbox. This shows my part list, my surface, my alignment. Someone spoke about creating your sewer along the road. We'll be using an alignment. We'll show you how to do that. This is where you do your part list. This is where you select your structure. So your structures are your manholes, right? So these are all sizes of the manholes that you can select. That just click that. So what I'm going to do is I'm going to select that, right? Then I come to my pipes. As you can see, I'm moving from 75 millimeters all the way to 1,500 millimeter PVC pipe. I'm going to select 160 millimeter PVC pipe because according to our standards, right, we need to have a minimum pipe diameter of 160. We can increase subsequently from there, right? So I've selected my pipe, I've selected my structure. I now come here and I click pipes and structures. And then this toggle is showing that I'm going from up, going to down. This is for deleting parts in a network. This is the panorama there where we can make some changes. More on that later. So what I do is the moment I click there, you can see my mouse cursor is saying specify the structure and session point, right? So I'll click there, right? There you go. As you can see, there's a structure. It's very small. It's very small, right? Then I click there, right? I click there, right? So as you can see, you guys, I've laid out my sewer there, right? And these structures are very small. Allow me No, I'm not going to make any changes to that. But anyway, as you can see, you guys, I just wanted, as you can see, I've got my structure details there that are showing the structure name. Let's just move it away from that. It's clashing a lot. Okay, that's showing the structure name, the ground level. This is your height in meters, the elevation, the depth, the invert out, right? Then here we're having that structure again. That's a manual. Remember, whenever we change direction of the pipe, we always have to provide for a manual, right? Right, there you go. I've got my structure, my ground level, my depth, my invert in, my invert out, right? We're gonna talk about that as well. Then the last manhole there, right? So that's how you do now, you guys. So after you lay out your what? Your pipes like that, right? I want to show you guys quickly how to draw them in profile view, right? You just click on any of them, you go to alignment from network, right? So I just select all the menus that are in that network that I want to do. I want to show them in that network, right? I right click, right? So it's probably, let's just say we're moving from menu 1 to menu 2, you guys, from menu 1 to menu 2, right? Then I'm not gonna have any labels there, right? I'm gonna add, then I'm gonna draw in profile view. Let's just say create, right? So if I'm creating, this is what this thing is like. This is how my sewer line is behaving. This is it in profile view. These are my menus and these are my pipes. And if you can go to your database, and this is called your database set, it has got your pipe gradient, your pipe details, your pipe depth, invert level, cover level, ground level. I've got my slope, I've got the length of that pipe, and then I've got the pipe diameter as well, right? So this is the information that we then take and feed into the hydraulic design to then analyze if this system can reach the cleansing velocity. Also note that my sewer system is been designed in such a way that it's following the natural ground level. Isn't this cool, you guys? Anyway, let's not talk about that. So this is how you do the preliminary design. So you start by doing the preliminary design. You lay out your pipes, you lay them out in profile view, then you start making the changes as you go. Now, this is the information that we're going to feed so that we do this is the information that we're going to feed in our code required so that we do the hydraulic analysis so that we can see if that pipe is meeting the cleansing velocity, right? Okay, so let's go back. Let's go back. Hydraulic design. You guys have an example for you, right? So what we want to do in the next 30 minutes, I really want you guys to pay attention. We are going to do a hydraulic design from manual 5.1 to manual 5.2, you guys. As you can see, this is how this thing was supposed to come out, right? This is my manual. These black dots are my manual, and these black lines are my pipes. So I'm going to design this pipe from this manual to that manual, right? So this pipe, as you can see, it has already been laid down, right? It has got a slope of 1:96. It has got a length of 65. And those are the details for this manual, and those are the details for that manual. All right. Okay. Great stuff. Great stuff. Great stuff. Great stuff. Right. The final product is supposed to be like this. The final product is supposed to be like this. All right. So good thing. I want to show you guys how we're going to do this real quick. Right? Hydraulic design, right? Okay. So whenever we're doing a hydraulic design, you guys, right? We have to understand that whenever there's a potable water that's coming in your house, right? It's 85% of the water that comes into your household is going to be generated as sewage. 85% of the water that gets into your household is going to come out as sewage. What I mean is that, hypothetically speaking, if we say there's 100 liters that's coming into your household, 85% or 85 liters of that water is going to go back into the system as sewage. So this is the equation there where we're saying bath is 25%, your kitchen is going to take about 10%, laundry and the likes. So all that water is going to make up what we call the gray water. Then the water from the WC, which is your water closet, is going to make up what we call the black water. So the total sewage is going to be 85%, right? Then we've got the average daily daily demand for each household. So for lower income households, right? For lower income households, you need to understand that we assume that each household is going to consume 500 liters per dwelling unit per day. For middle income, it's going to at least consume 750 cubic meters per dwelling unit per day. Then for higher income houses, this is your low density suburbs, right? That you have got a an average square stand of at least 1,000 square meters. So they're going to have at least 1,000 liters per dwelling unit per day, right? So if you want to calculate this, remember we said we have to calculate the amount of flow that is being what? That is being produced by this house. So you calculate what we call the average dry weather flow, right? Which is your consumption multiplied by the return flow, which is the 85%, because we made an assumption that 85% of that water that gets into a household is going to be generated as sewage, right? So we're saying for this household, right, for each household, if it consumes 500 liters per day, so how much liters is going to be generated as sewage? So we say 0.85 by 500, we get 425 liters per day is going to be produced as sewage, right? Then after you do your average daily dry weather flow, excuse me, right? After you do your average dry weather flow, you do what we call your peak dry weather flow. So we also have to account for peak factors, right? You have to understand that people are not going to all go to take a shower at the same time. People are not going to do dishes at the same time. But we can, by general approximate when we're going to have peak factors. And by culture, usually we're going to have peak factors in the morning and the evening. Usually in the morning because people are preparing to go to schools, people are preparing to go to work. So everybody's taking a shower, people are cooking. So we're bound to have peak factors. And we're also going to have peak factors during the night. Everybody's back at home, they're preparing dinner, some are doing laundry, some do laundry every day. So we need to account for the peak factors. So we use a peak factor of 2.5. Of course, there are manuals that go into us determining the peak factors. We're not going to talk about it today, but you just need to know that when you design our source system, we design with a manual, right? Okay. So we use a peak factor of 2.5. So the peak dry weather flow becomes 2.5 multiplied by the average dry weather flow. Then after we do the peak factor, then we do what we call the peak wet weather flow, right? So the peak wet weather flow is now taking into account the water that infiltrates into your sewer system due to leakages and due to manholes. So your stormwater, no matter you like it or not, is still going to infiltrate and find itself into your manhole. So we need to also account for it. Though it's not ideal, but we just need to account for it. We always design for the worst case scenario, right? So your water is still going to infiltrate your system, right? So that's the peak wet weather flow. We have a peak factor of 5.25, and there's a whole explanation of that according to our SALA manuals and according to our DWG manuals and according to our Red Book manuals. We all have this sanitation and design planning. It also talks about how you come up with those peak factors. So this is your hydraulic Manning's equations. So for Manning's, we'll be using that Manning's coefficient. For Cobb required, like I said, we are going to be given these values. We're going to be using 0.6, right? Then this is also from the manual, you guys. You don't need to worry about that. So it's telling you that if you're using a pipe diameter of 150, your minimum slope should be at least 1:200. These are your minimum slopes, you guys. So till now we have got a minimum pipe diameter of 160. We do not have 150 in the market, so we start from 160. So we're just going to assume that our minimum gradient should be 1:200. So we're sorted in that regard. So you have to understand that your sewer will be increasing in pipe diameter as we go down the slope, but we're not going to touch about that. So this is your Kolb-White equation, as you can see right there, right? So now I just want us to get to the manual calculations of this thing so that you guys can see what I'm talking about, right? Cool. So design is sewer line manual between manual 5.1 and manual 5.2. So the design a suitable pipe for that low income housing scheme. So the low income implies that we have got at least 6 people that are living in that house. So the consumption becomes 600 liters per dwelling unit per day. Remember, according to the manuals, according to the sanitary design manuals, they're saying for low income, you should have at least 500. So your 600 here won't be a train smash. You won't go to prison for it. It's still fine, right? So we're having a consumption of 600 liters per dwelling unit per day. How many housing units are we servicing? So we go back to our example. So remember, you actually do the preliminary design, right? You lay down your pipe. So this pipe is servicing how many stands? By servicing how many stands, we're saying You see these arrows that you see, these little baby arrows that you're seeing there, those are your stand connections. Those are your sewer lines that are going to be connecting from this house, from this house. So this house, this house, this house, this house, all these houses here between these manholes, they're going to be connecting into that pipe. So which means all the water that we're going to be flushing, all the water that we're going to be producing is going to be collected by that pipe. Therefore, for us to properly size that pipe, we need to know how many stands are feeding into that pipe, right? So we have to count 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 times 2, right? So that's 18 stands, right? So we've got 18 housing units between manhole 5.1 and manhole 5.2. So now if we want to calculate our average dry weather flow, right, from that equation, so we say 600, each housing unit is producing 600. So for 18, we say 18 by 600, right? And that total amount, we multiply it by 0.75 so that we can get this return flow, the amount of sewage that we are actually going to get. So the amount of sewage that we're actually going to get is given by that formula, which is 9,180 liters per day from 18 houses. Then if we convert, we always work in liters per second, which means we are going for 18 houses. 18 houses, they're going to produce 0.1063 liters per second, or it's going to produce 9,180 liters per day, right? Take note of this. Then we apply our peak factors. There's a reason why we applied 3.5 here, because of the population factor, right? So the peak factors also take into account the population projection. We did talk about the fact that whenever we're designing our sewer, we need to take into account the future generations. So we know that our population is going to grow, right? People are going to be born, blah, blah, blah. People are going to move in, urban migration, things like that. So this peak factor accounts for that, right? Then, so for you to get the peak dry weather flow, you then multiply the peak factor, multiplied by what? Your average dry weather flow. So we're saying per day, this is what 18 housing units are producing. So what is the peak? If we factor in the peak, we're then saying 3.5 multiplying by that, we get that. So we're saying if we factor in the peak and we also factor in people that move in and the population growth, we're going to get 0.372 liters per second. This is per day, by the way, right? Then after we do that, we factor in the peak wet weather flow, which is we multiply by 5.25. So we're multiplying our peak dry weather flow with our peak wet weather flow factor, right? So that we're going to get 1.195. So you guys, we've added our peak factor, we've added our peak wet weather flow. So we ended up getting 1.95 liters per second. This Q is called your design flow. This is the peak flow. So this is the amount of sewage we need to expect. Excuse me. Okay. So this is amount of sewage that we are going to expect. You guys, the peak design flow, right? Now that we have got our peak design flow, we have got, we have the slope. We did the preliminary design, right? Remember, we have the slope, you guys. Let me expand this so that you guys can see. I hope you guys, that's better, right? We have our slope, you guys, this slope. 1:96. We have the length of that pipe, right? And we have the diameter. What did we say the diameter is, right? The diameter we said is 160. Remember, I said we use a minimum of 160 millimeter pipe diameter. Extend connections are allowed to be 110. So more on that is all in our manuals, right? So let's go back to the example. So now I have my slope, right? I have got my length, right? I've got my diameter. What else do I need? Nothing else. I can now plug in all those values into my Kolb-Required equation. Let me expand this for you guys to see. I can now plug in, I've got G, I know G. D, I have it. Slope, I have it. The kinematic viscosity, I have it. This K, which is 0.6, I have it. D, I have it. This D again, I have it. G, D, I have all these values. So what I simply do is plug in all these values that I have. Remember to always make your conversions correctly so that you don't get weird values. So if I plug in all my values there, I then get my cleansing velocity, right? I get my velocity. So using the Kolb-Required equation, we can then calculate the V, which is your full bore velocity, right? Take note of this value, right? I need to explain this again. Please, 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 please pay attention. Right, this velocity is called the full bore velocity. Right? If you notice, we took the entire diameter. So by us taking the diameter of 160, we're assuming that this sewage is flowing at full bore. So whenever you make your sewage design, right, we always assume that our sewer is flowing at full bore, which means it's flowing at full capacity. It's full. There is no space in that, right? So if it's flowing at half bore, it will be something like this. This is half bore, you guys, right? Those small dots. Okay, let me try and pick another color. Oh, these colors are not doing me any favors. Eh? So I'm trying to say all this here. This is your sewage here, right? Then at quarter bore, it will be probably somewhere in there, right? Which means the sewer is flowing at that depth, or this is empty. This is at half bore. This is the sewer, or this is empty. This is at full bore. There is no empty space. So whenever we're using the Colebrook, right, this is why we're taking this D, right? We're saying this D, which is the diameter. We're taking the entire D. So by virtue of us taking that full D, we are making the assumption that we are analyzing this sewer at full bore. Why do we do that? Someone might ask themselves. Sorry about that. Why do we do that? So whenever we are analyzing our sewage, we're analyzing it full bore because we are saying our sewage is going to reach full bore conditions at least once or twice a day. What does that mean, you guys? Right? Remember, I will take you back to that illustration that I made when I said when we're laying our pipes, right? That's my main hole there. That's my main hole there, right? Then I'll have my natural ground level there, right? Going there. So I was saying I was too lazy to go outside to dump my leftover lasagna. I just flush it down the drain, it will settle. So because I'm the only one who's doing dishes, I'm not producing this amount of peak discharge. This is what I need you guys to know. It's not ideal that all the time we're going to produce this amount of peak discharge all at once, because not everyone is going to do dishes at the same time. Not everyone is going to take showers at the same time. Not everyone is going to do laundry at the same time. So this sewage is not all going to be produced at the same time. So what happens is that if I go to the toilet or if I take a shower, probably I use 80% or 80 liters of water just to take a shower. 0.85% of that water is going to be generated as sewer, right? And then it's going to be flowing into my sewer line. But that water does not necessarily mean it's going to reach cleansing velocity already. Please take note of that. You understand? It does not instantaneously reach cleansing velocity because it does not have sufficient flow for it to reach cleansing velocity at one very go of its production, right? So what happens is that, okay, fine, I do what I do, then I drop my spoon there, right? Because it's only me who's doing dishes that time. There's only little water, so that water does not have enough energy or velocity to push the spoon down or to push the sand down. So what's going to happen is that sand is going to gradually collect. Someone drops their soap down the drain, it's going to gradually collect, right? Then what's going to happen is that these sediments, they're going to accumulate like that. As they accumulate, please take note of that. The diameter of that pipe is going to gradually being reduced, right? So what happens is that now it's now 6 p.m. Now everybody's back at home, everybody's taking showers. Then there is that peak thing that we talk about, the peak factor. Then when that peak factor, there's a lot of sewage that is being generated. Therefore, yeah, your sewer will achieve full bore velocity because now, because of that reduced diameter of the pipe, water is going to be forced to flow just with that small pipe or that small space that's left. Because of that pressure now, it's going to force all these solids to be pushed down the drain. So what we're saying is, if your pipe is going to achieve full bore velocity at least once a day, what is that full bore velocity? So according to this calculation that we made, we're saying that full bore velocity is going to be 0.93 meters per second. What is the minimum cleansing velocity? I was hoping that someone was going to ask me that question because we've been talking about the minimum velocity all the time, right? We talked about the minimum cleansing velocity. If we get back to this question here, we'll get back to the definition, right? We said in sewer system refers the minimum flow velocity required, minimum flow velocity. So what is the minimum flow velocity that's required? So the minimum flow velocity, you guys, ranges from, excuse me, your minimum flow velocity ranges from 0.7 meters per second, right? That's your minimum velocity, maybe to 0.75 meters per second. It depends with manuals, right? Right. In this manual called the Sala manuals, they've got a minimum velocity of 0.75 meters per second. That's your minimum velocity, right? In our sanitary sewer design planning, they've got a minimum velocity as 0.7. Some have got minimum velocity as 0.6. So we're just going to work from 0.7 to 0.75. So we are saying that we need to calculate our full bore velocity such that it falls within the ranges of 0.7 to 0.75 meters per second. So this is the recommended minimum cleansing velocity that we are calculating. However, from the stuff that we got, using these parameters that we have here, the full bore velocity that we are getting is 0.93 meters per second. This means that this sewer line can reach cleansing velocity. It has got the ability to cleanse itself because it is way above the minimum required cleansing velocity. I hope you guys understand that. So this is the full bore velocity, right? This is the full bore velocity. So from the continuity equation, right, Q is equals to VA. I'm sure you guys know this from your fluid mechanics, right? We have got our velocity there and we have got our area, right? The area of a circle is what is pi d squared over 4, right? And the diameter, we already have it, which is what, 160. We can be able to calculate our full discharge, right? So from the cleansing velocity, if I'm having a cleansing velocity of 0.93 meters per second, which means the full discharge of that pipe will be 18.76 liters per second, right? So which means if this pipe is flowing at full capacity, it will be flowing at a speed of discharge of 18 liters per second. Yo, that's fast. That's a lot of, yeah, that's a lot of energy right there, right? So if it's flowing at full discharge, the capacity is going to be 18 liters per second at full bore, right? So that's the capacity, that's the full capacity of this pipe. But we said the maximum capacity of this pipe, of the maximum sewage that can be generated by 18 households is what? Is 1.9 liters per second. But the full capacity of the pipe is what? 18 liters, 18.7 liters per second. So which means this pipe has got the capacity to carry this sewer. It's way able to carry the capacity, this sewer. So the big Q, which is your full bore, is greater than your small Q, right? Your big Q, because the big Q is the discharge at full capacity. This small Q is the maximum discharge produced by 18 housing units if we factored all the peak factors. Therefore, what it means is QQ is greater than Q small. Therefore, this sewer line has got the capacity to carry the sewage. So the capacity check is done. Then if we go to the cleansing velocity, the velocity that we're getting, this one is greater than 0.75, right? Therefore, this sewer system has got the capacity to what? To cleanse itself. Check. So therefore, the conclusion is that this sewer has got or has reached what we call self-cleansing velocity. That's how you do the hydraulic design of a sewer pipe. So this, according to these parameters, right, this sewer line has reached cleansing velocities. So we are good. Therefore, if you're now designing a sewer system, then you do this, you repeat this process for this pipe, you repeat it for this pipe, you do it for this pipe, you do it for this pipe. So you do it for each and every pipe. Therefore, that exercise becomes a very tedious exercise. We need to find a way of automating it. Therefore, you have to create your Excel spreadsheets. You have to create spreadsheets, you guys, so that you can automate that process right there, right? So this is where you start using your Excel spreadsheets for you to do that process, right? So you guys, I've just showed you how to do it. I've just showed you how to do the hydraulic design. So that's hydraulic design in a nutshell. But now that you've calculated your cleansing velocity, yes, it's being met, it's 0.93. Is it the optimum velocity that you can get? By optimum, I'm saying the slope that you have, this one, this 1.96, this 1:96, is it the best slope that you can have? Because 1:96 is pretty steep, you guys. Remember, I'm using a pipe diameter of 160, and the minimum gradient I can use is what? Is 1:200. So I have leeway to go as flat as I can, because you have to understand that the steeper you dig, the more expensive your project becomes. The steeper the slope, the steeper the slope, the greater amount of earthworks you're going to produce. There's a direct link between your slope and the amount of earthworks you produce. And also, there's a direct link between your slope and the cleansing velocity. So this is where now you have to be very, very clever, because you have to sort of like strike what we call a happy medium, right? You have to satisfy both ends. Your sewer system does not have to be too steep, right? Such that we have to dig. Let's say we're having our natural ground level like that, right? Your sewer system doesn't have to be too steep, right? Such that we are having very deep locks and in very deep trench excavation like this. This is steep, you guys, right? So it doesn't have to be too steep. You'd realize that this maybe might be 2.5 meters to 3.5 meters. If you want to know how deep is 2.5 meters or 2 meters, just look at the door in your room. That's 2 meters right there. So imagine us digging that 2 meters for a pipeline, let's say that is 56 kilometers. That's a lot of money. So if it's too deep, right, which is to say your pipe is too steep, which means your trench depth will be very deep. But if it's too flat again, which means it's going to compromise, it's going to compromise your cleansing velocity. So if it's too flat, then your cleansing velocity will what? Will decrease. I'm sure you guys watched when there was an illustration in that video that if you decrease your slope, then you also decrease the cleansing velocity in that pipe. So you need to strike a happy medium here to say your sewer doesn't have to be too deep, your sewer doesn't have to be too flat. It has to be flat enough such that your pipes can achieve full bore velocity, but it doesn't have to be too deep. Therefore, it can make the whole project very expensive. So this is what I want you guys to look like. This is the final product that you should get. You see, look at that sewer system that we designed there. Look at that, you guys, right? We're having a slope of 1:200 and a length of what? 73. So for a slope of 1:200, you can actually get a cleansing velocity of 0.741. If you are to do your own calculations, I dare you, if you want, I'm probably gonna provide you with this with these notes. Try and calculate your hydraulic, do your hydraulic analysis for all of these pipes and see if they meet the cleansing velocity. You see, and as you can see, according to my design, you guys, according to my design, I designed in such a way that I'm having the least possible slope I can have, because this is 1:200, right? But at the same time, I'm following the natural ground terrain. As you can see, that's my natural ground terrain there. And then when it changes to be steep there, I also do the same thing, right? So this is where you guys need to be very, very clever and very careful, because your sewer line and your sewer slope should also follow your natural ground terrain, right? So this is, I also showed you how you produce this in your Civil 3D. So this is your, what you call your data bin set, where we have our chainage, we have our ground level, we have our cover level, we have our invert level, we have our depth, right? We've got the pipe gradient and we've got the pipe details. All this information is needed by the constructor during the construction phase. And this is in meters, your elevation is in meters there, right? So guys, this is literally, that's it. I just did an example of designing one sewer pipe. So what you can essentially do is you can challenge yourself and then design the following, this one. But there's a trick to it. If I'm now designing this pipe from men 05 to men 05 to men 05, the number of stands that I now use is no longer 18. I now say 18 plus what? Plus this amount of tens, which is 1, 2, 3, 4, 5, 6. So it becomes 18 plus 12, because the amount of discharge that is carried by this pipe increases as you go downstream, right? It increases as you go downstream. Okay. So guys, those are just, like I said, today we're just touching on the fundamentals, and I just did one brief example to show you how to do that. But there's a way to automate this, to actually do a spreadsheet, and there's a way to do this in a much economic and faster way. So just to polish up this whole thing, the fundamentals is your slope, your pipe diameter, the amount of sewer that needs to be produced. So in as much as you are done designing your sewer, you should have something like this. This is the quality and the standard of work that you should produce, the final product, which is your construction drawings. Excuse me. Right, so this is the final product that you should get. So for the next I don't know, I have 4 minutes, I guess. Let me just look into the chat box to see if I've got question or someone is saying you can't see. Okay, does the Kubrick equation assume full flows in pipe? Yes, it assumes full flows in pipe, because whenever we're designing our source system, I mentioned this, we assume full bore capacity, right? Our flow, we assume it as full bore capacity, right? Right, do not clearly understand the base of your question, but sanitary sewer is an open flow system. It ideally never. Thank you. She actually answered my question there. Raymond, thank you for that. Right, that's a good question. Can you please share the hydraulic design PDF? Sure thing, I'll do that. Does Autodesk Civ 3D 2021 have all these tools? As long as it's called Civ 3D, it has these tools. But we always encourage you to use the latest tool because it's quite cool, right? Yes, it does. Someone answered, okay, right? Then there's Jerome. How do you determine your slope, diameter, your diameter? Do you use the lowest value, then optimize it that way? So like I said, first of all, you start with the preliminary design. So you actually design it in Civil 3D. You draw it, you do your sewer layout, you do your profile views. Then you take those slopes. You'll be using your mind, and you're also using, because this is where you have to be present. Like I said, Civil 3D does not design, you design. So you'll be looking and say, okay, fine, does this slope make sense to me? Because you don't want to lay a sewer that has got depths up to 10 meters. So you see, okay, this slope, it gives me at least maybe depths from 0.8 to like 1.2. Okay, let me try and use this slope. Then you assume your diameter of minimum diameter of 160 millimeters. Then you plug in into code required to see if that pipe can do the cleansing velocity, right? Then you start optimizing. So you'd realize that whenever you're doing your sewer system, it's an iterative process. You just don't do it once and you're done. You first of all do your preliminary design, you do your hydraulic design, and if it fails, you do again until you get the correct cleansing velocity. So it's an iterative process for you to actually get an optimum value. Do we have a maximum velocity to prevent solid segregation? That's a good question. So your maximum velocity is 3 meters per second. It's not actually solid segregation. We actually want the solids to separate as much as we want so that our sewer mixture can become homogeneous. However, if we have solids that are greater than 3 meters per second, your silage or your water, it is now flowing at a very fast it's now flowing at a very fast velocity such that it actually starts to leave behind the solids. You understand what I mean? So we're saying at more than 3 meters per second, right? What happens is that your sewer system is actually flowing at so much velocity that the particles cannot keep up with the flow of the water, such that they will be just what will be left behind because it's now a pipe jet. You get my point? So at more than 3 meters per second, the solids will be left behind because they cannot keep up with the speed of that fluid, right? And it can also cause what cause scouring for our manholes and our pipe. It bends. So I've never designed a sewer system that reaches 3 meters per second. Even if you include your pump main station, this is where maybe you've got the danger of hitting high velocities like these ones, but they always have to be below 3 meters per second so that we don't have scouring, and also so that we don't have a water jetting that leaves your solids behind. Anyway, that was a good question, Jerome. That was a good question. So let me go back and see where I was. All right. Yes. Then Damien said, what is your suggestion on the guide that doesn't allow sewers to fall through? No, here's the thing. Whenever you're designing a sewer, the assumption is that they're flowing at full bore, but they never actually flow at full bore in actual reality. They only flow at full bore only when it has reached its cleansing velocities during its peak factors. That's at least twice a day. So it's actually a good thing that it flows at full bore. So here's the thing. Suppose your sewer is flowing at full bore. Another thing that you need to understand, guys, about manhole is that they act as a temporary storage. So here's the thing. What happens is that your sewer is flowing and it's full in this pipe, right? Assuming this pipe is overwhelmed, it's full. So what happens is that when it gets to this point, the sewer will start rising in the manhole here. So the manhole can also act as a temporary storage if the sewer system is overwhelmed, such that during peak times, the sewer levels will rise in the manholes here because it's flowing at full bore here, it's flowing at full bore. So there's not enough space for the sewer to flow. It will start just to rise in the manholes like that. And then when the peak factors subside, then that sewer will start to decrease and flow nicely. So that's also another way we also need to provide for manholes because they also will act as your temporary storage. Okay, right? Let's see. I hope I was not lost. Let's see. All right. Do you redesign using slope as per recommended pipe diameter? Yes, that's what you do. We said it's an iterative process. What is the roughness of the pipe? So according to the code required, we use 0.6. So you're given the roughness of that pipe. So for your Mannings, it's 0.006. For Colebrook, it's 0.6, right? Right. Roughness, we do not assume 100. This is for the Hayes and Williams when you're doing your pipeline design. That's your potable water design. So it's not 100, right? Michael's Banda is not 100. It depends with the equation that you're using. So you'd realize that when you're using the Hayes and Williams, the Hayes and Williams coefficient for new pipes is 100, but in the Colebrook, it's 0.6. So please take note of that. So the roughness depends with the equation that you're using and the pipe material that you're also using. So you'd realize that if you're using the Strickler equation or the Scooby equation, they would suggest a different ranges of the roughness that you're going to use for different pipes. So you'd realize that back in the old days, they used to use the AC pipes. That's your concrete pipes. So they have got a different roughness. Okay, my time is up. Just 5 more minutes. For this design, since we are unable to obtain the data, can we use the slope in the profile view? Yes, that's the whole idea. You actually use the slopes that you provide. Like I said, you start with the preliminary design. You suggest the slope, you suggest the diameter. Then you do an iterative process until you have an optimum slope that gives you a cleansing velocity. At the same time, it's not too deep for your trenching. All right. So this data, you come up with it yourself. That's the whole sense of design. That's the whole soft direct. We're talking about softwares. Yes. So there's a plugin with 3D called SSD. It does do your hydraulic design. More on that. Of course, that's only preview for the guys that actually subscribe for the course, but we're going to touch about that. Please, can we have the recording? Yes, you are going to have the recording. As long as you're part of our Roads Hub, our communities and all the Telegram group, you will have access to the recording. Don't worry about that. Not a question, but rather a comment. We need Civil 3D course. Yes, it's coming. It's coming. If you just go to Roads Up, man, everything is there. All right. There is your highway there. There's gonna be your sanitary there. So yes, it's coming. I'm sure you're talking about the course. It's coming. You'll be notified when we're doing the courses. The calendars will be released for you guys. So don't worry about that part. Please, may you share the sanitary sewer design manual. No problem. You can hit me up. I can share with you. Can we please get the contour file you are using? Unfortunately, I cannot give this one. It's an intellectual property. But if you want something for practice, I can make a plan for you. Okay. How can we get the practice file that you said earlier? This is Felix. So I'll produce, okay, the stuff that you can use. All right. I think that's fair. What would be the difference between the hydraulic calculations using the Manning's formula? That is a good question. So I actually did not get the chance to cover that, but I have done it in the Manning's formula, and I've also done it with the hydraulics formula. It's quite different, but it's still the same thing. And the differences in the results is because of the assumptions that you make in the two equations. But eventually you still get the same thing. But there are differences that can be explained. Unfortunately, we did not touch on that one, so I won't be able to answer that because I do not have the results for the Manning's equation. But I did mention that the Manning's equation is very sensitive to small changes. That's why I seldomly use it. Okay. The Brook formula is more accurate and it has less deviations. Thank you, Mike Spander. That is very correct. What methods can be used to quantify and mitigate the effects of infiltration and inflow using sanitary? That's a good question. um, well, I can just simply say maybe tighten up your screws, tighten up all the joints in the system. Just make sure that all the joints are sealed and they're quite tight, and also make sure that your manuals they're also quite tight as well, right? Yeah. Also try and make sure that your sanitary source system uh does not follow the terrain of the lowest possible area, because if it's flowing the lowest possible area, in lowest possible areas, there tend to be a lot of ponding when it rains. So when it rains and there's ponding and there's like a manhole there, water will naturally trickle in into your manhole and act as a catch basin, right? Thank you. What would be the best depth you would recommend, or the minimum depth? Okay, this is also part of your this is part now of the design manual. We're probably going to cover this in depth, but roughly speaking, we're talking about from 0.9 to a maximum of 2 to 2.5. It should not be greater than that, right? There is a link there to join our community, right? All right, guys, I'm running out of time. So I think the best thing that you can do, okay, it's just two questions that are left. All right. In your long section, would you indicate the flow direction? Also, also not be a good to sort of have full and partial flow comparison of Q over Q along the line, thus to have an idea of your flow capacity, or does Civil 3D do not allow for this? The thing is, this was just the fundamentals, guys. We do what we call the capacity analysis in the design. We do talk about that, and we do teach that in detail. And we also didn't, there's a lot of things that we did not touch about today. We did not touch about the standard details. We did not talk about our SWA connection. We did not talk about the direction. Today it was just about the fundamentals, just to introduce you and have a feel of what SWA design is all about. So we didn't even cover 30% of what SWA design is all about, but this is just sort of like an introduction to the whole thing, right? Okay. Then are you the one that determines the path of the SWA line, or the surveyor? What are the considerations before position? I'm the designer, remember. I'm the one that actually determines the path of the SWA line based on my surface analysis. This is where design comes from. The surveyor does nothing here. You are the engineer, the ones that actually what determines the path of your design flow, of your design line, right? So it's the engineer's job. So it's part of the design. So you have to first of all do your surface analysis, see how your flow lines are going, then decide the path for that sewer. Guys, wow. Thank you so much. Thank you so much for attending today. This marks the end of our design challenge. So do you want to master sanitary design? Enroll for our upcoming courses. So you guys, you will be told about this, okay? We'll keep you guys in the loop. So this was just the basics. We do teach you SWA design so that you can master it, and so that you can actually design it in your companies and your works, and you surprise your boss by coming up with a very cool idea. So I'm going to share some of these files. Please, guys, take action now. Thank you so much for attending. I appreciate you guys. Thank you so much for being part of our opportunity. Thank you so much for the Roads Up team for giving me this opportunity. Engineer James, shout out to you. I'm signing out. Thank you. Cheers. Bye.
Thank you very much, Baron. That was a super amazing webinar, very loaded with a lot of information and knowledge. I also want to thank the participants for being exceptionally active. I like your questions, very, very, very curious, very knowledgeable, and it shows your great desire to learn and improve your skills. So thank you very much. Just like Baron said, Baron, I don't know how much we can thank you, but that was a super amazing design challenge. So this is gonna be happening every Friday, every Friday, every Friday. So come with us, let us learn, let us grow together. And just before I go, we'll be having also a course that will be opening very soon on storm sewer design. We'll keep you on the loop as well, because the whole point is for us to learn and grow. So thank you very much. Thank you, thank you, thank you for everyone who has been involved in planning, in designing, and most importantly, of course, our guy, Baron. So thank you very much. Thank you very much. That was a very brilliant session. We'll be having a lot more coming to you guys. So thank you. Stay tuned, and may we all have a fantastic night. If you still want to access our other courses, which I think also you would be interested in, so all you need to do is you just go to, let me show you guys. You just go to Google or whatever search engine you have and search Ron's Hub. And once you search Ron's Hub, you just go to our website. So you'll be able to go to courses. If you go to courses, you can be able to see the courses that are currently on offer. So we have the Ultimate Civil 3D for Road Design course. This is a course for you to learn at your own time. So it's the same training that we offer for road design. We have packaged it for people who are from different zones. People are very busy. They may not be able to join our program. So you can be able to do that. Just purchase the course and learn at your own free time. It has all the design concepts, it has learning materials, the manuals, it has the videos, it has even sample design that I have been able to work on, that the captains have been able to work on as well. So yeah, you can be able to access basically everything. The beauty of it also, you can just click on it to look at, for example, the things that you'll be able to learn. So you can be able to see the things, what you'll be able to learn, materials included, requirements, and all the course outline. So feel free to interact with it. Refer to other professionals who would want to learn. So for this one, I'll just type it in here. If you're interested, you can be able to get the course at your own time. That's right there. And then the other one is, if you go back, you can be able to access, for example, book the Civil 3D training for September. So we have a Civil 3D training for September. It's right here. You can be able to enroll and then you join the waiting list. So that's it from us. And also the course on Storm Sewer will also be uploaded here once it's prepared. And keep interacting with us, and we really appreciate. We look forward to building you guys. We are now Autodesk certified. We give certificates for every courses, even the courses online. You'll be able to get your certificates for sure, for sure. So keep building your skills, be able to reach out to us, interact with us, engage with our community, and we are here to serve and give you the best experience possible.